Khufu's Great Pyramid required approximately 2 million stone blocks to build. At the peak of construction, workers were setting a 2.5-ton block into place every 12 seconds, amounting to 5 blocks a minute. 4,500 years later, the mechanical logistics required to maintain this speed remain unexplained. This lack of a clear answer stems from a literal error in perspective. Historically, researchers have only ever analyzed the exterior walls. Relying on the visible surface of the structure has obscured the true architectural realities hidden just behind the facing stones. The most widely accepted historical explanation is the long ramp theory, but it relies on a hard physical limit. If a ramp's incline exceeds 8%, a team of workers cannot drag a heavy stone block up the slope. When you apply an 8% grade to a structure that sits 481 feet tall, the ramp itself would need to be over a mile long. It would require more material than the pyramid itself and obliterate the adjacent cemeteries on the Giza Plateau. To solve the space problem, archaeologists proposed the spiral ramp theory, wrapping a smaller ramp around the pyramid's outer faces. This digital 3D model illustrates how the spiral design fails on geometry. Architects had to constantly monitor the angles of all 4 faces to ensure they met perfectly. A ramp hugging the outside hides the corners, making precise measurements impossible. Because exterior physics eventually fail, the structural solution must exist within the stone itself. In 2003, French architect Jean-Pierre Houdin took a different approach, using modern 3D architectural rendering software to digitally dissect the monument. This structural rendering illustrates Houdin's proposition. He suggests the builders used a small external ramp for the bottom third, but finished the top 2/3 from the inside out, using an internal tunnel winding upward at a 7% grade. This introduces a severe mechanical challenge. A tunnel inside the pyramid would be narrow. Turning a 2.5-ton block 90 degrees at each corner seems physically impossible. The physical evidence sits 270 feet up the northeast corner of Khufu's pyramid. There is a distinct weathered notch left open in the stonework. When Egyptologist Bob Breyer climbed up to inspect the floor behind this exact notch, he found an undocumented room shaped like an L. This shape is functional. The L-shaped corridor provides the exact spatial clearance required to install a wooden crane, hoist the blocks, and pivot them 90 degrees to align with the next upward section of the ramp. Discovering purposeful, hidden spaces inside the masonry provides a mechanical solution that external theories cannot offer. This architectural model aligns with data gathered decades earlier. In 1986, a French survey team used microgravimetry, a technique that measures slight variations in density, to scan the core of the Great Pyramid. The scan detected a massive structural anomaly. The data showed distinct patterns of lower-density material spiraling upwards, parallel to the outer edges of the monument. Those low-density spirals matched the exact projected path of Houdin's internal ramp. These scans provided a bridge between architectural theory and the physical reality of the internal construction. We're continuing to find hidden structures today. In November 2025, the Scan Pyramids project turned its attention to the smaller Menkaure Pyramid at Giza. Researchers focused on the monument's eastern facade, an area covered by massive, highly polished granite blocks. To see behind the stone, they combined ground-penetrating radar and ultrasound testing. This elevation blueprint of the eastern facade highlights the findings. Instruments detected 2 distinct air-filled voids located 1.3 meters behind the solid granite. Simulations confirm these voids are too geometric to be natural cracks. They are deliberate internal spaces. Examining these monuments as multi-layered structures continues to expose engineering decisions hidden just beneath the surface. The Great Pyramids function as highly sophisticated, intentionally hollowed structures. By combining 3D modeling with advanced image fusion technology, we can digitally peel back the limestone to map the complex engineering hidden inside. The era of destructive archaeology is coming to an end. We no longer need to dismantle ancient walls to understand the methods behind them. The most detailed truths about our ancient past are now being found by looking through the stone, rather than just at it.